After watching the video lecture, students will be able to describe spontaneous processes, explain the relative entropy of specific systems, and of course relate entropy to the spontaneity of a process and the second law of thermodynamics. So at this point, we have covered lots of different approaches to analyzing chemical processes. We've looked at them from the perspective of kinetics, which basically analyzes the speed of the process or the rate of the process. We've looked at equilibrium, which indicates the degree to which the reaction progresses. And of course, we spent some time looking at thermochemistry, which analyzes the heat transfers associated with specific processes. So we've learned all these skills relative to speed and degree of progression and of course heat exchange. So we're pretty competent in terms of analyzing specific reactions. And if we look at the examples that have been provided below, we have the neutralization of a strong acid and strong base, and basically the dissolving of salt into water. Okay, and both of these processes readily occur. They occur pretty quickly. The position in terms of equilibrium lies pretty far to the right, meaning that we go to products pretty readily. And if we look at the enthalpy values that are connected, or at least their signs, we see that one of the processes is exothermic, one of the processes is endothermic. Now, these reactions occur. We know that they occur. However, none of these indicators up here help us identify why these happen, okay? And so these processes, because they just occur on their own, are known as spontaneous processes. And a spontaneous process is a process that happens or occurs without any ongoing outside intervention. So basically, I mix the acid and base together, the neutralization occurs. I put the salt into water, it dissolves into its component ions. Okay, so these spontaneous processes just happen, they just occur. Now, the spontaneity of these processes are directional, meaning that the spontaneous reaction process is always going to be in one direction, and then generally the reverse direction is non-spontaneous. So if I put sodium chloride and water together in a beaker, they're not going to come together and produce HCl and NaOH to any appreciable amount. So now that we understand that processes can be spontaneous, the question that should be coming up is, why are they spontaneous? What is driving it? So we have relatively quick processes up here. We know that equilibrium lies to the right here. We have different signs in terms of our thermochemistry, in terms of our enthalpy value. So it's not any of these features or these ways of analyzing chemical processes that are getting us to why this process happens, okay? And so the answer to why a spontaneous process happens is a thermodynamic feature called entropy. Okay, and so this is something we've looked at a little bit before, but we're going to talk about it in great detail. So entropy is a thermodynamic function that's going to increase with the number of possible ways to arrange the components of a system. Okay, so basically a nice way or simplified way of looking at entropy is basically that it's a measure of disorder. So the more disorder you have, the more entropy you have. Okay, and so this disorder or this entropy is the driving force for why processes just naturally occur. Okay, so the spontaneity of a process is dictated by entropy. Okay, now entropy is a state function, meaning that we don't really care about the pathway that it takes in order for us to get from our starting position to our end result. All that we care about is the final and the initial state. And the difference in the final and initial state is going to give us our change in entropy. And the change in entropy, if the value that we obtain from taking the difference between the final and initial state is positive or greater than 0, the entropy of that situation has increased. If it's negative, the entropy has decreased. Okay, so we have some intuitive examples of entropy increasing. Your mom tells you to clean your room, you get it nice and organized, but as you progress through the week, you're using your room, you're studying, you're leaving things out so you can go back to it, and basically things become cluttered and disorganized, and basically your bedroom by the end of the week is super disordered. So the entropy has increased massively. If you've ever played with a deck of cards, maybe a card game, you know that as the game progresses, you go from a nice little stack in the middle of the table to basically, misshapen piles. Okay, so these are examples of entropy or disorder. Okay, so now we're going to look at a couple of different ways of analyzing disorder. Okay, so basically the more arrangements or positions or energy levels that are available, the more likely a process is going to happen. Okay, so basically we define a state as a particular arrangement, and a microstate is the number of ways that arrangement can happen. Okay, so if we look at the example over here on the right-hand side, basically we have 3 different states, so 3 different particular arrangements. Okay, we have the balls all on one side. We have 3 and 1 as a secondary arrangement, and the tertiary arrangement is we have 2 and 2. And of course the colors of the balls are helping us differentiate between various organization patterns. Okay, so now that we've looked at the states or the particular arrangements, if we look at the types or the number of ways that can be met for each example, we then run into microstates. So if we look at each of these individual states, what you notice is, okay, we have one arrangement, okay, basically 4 balls on one side. We have the next arrangement, which is 3 and 1, and the arrangement after that is 2 and 2. Okay, so basically what you should notice is that the number of ways of arranging, or the microstates, is increasing as we progress down the particular states. Okay, so notice here we only have 1, here we have 4, here we have 6. Okay, so the number of microstates are increasing in each of these examples. Now, we know that the more arrangements we have, the more likely the process is going to happen, right? So more disorder, more likely something's going to happen. So in this case, state number 3 is most likely the one that would be reached by the balls in this container when compared to state 2 and 1. So this is just an explanation or analysis of disorder from one perspective. Now we're going to go ahead and look at it a little differently. Okay, so another way of looking at disorder is basically the movements associated with specific molecules. Okay, so I'm going to go ahead and first start with translational motion. Okay, so translational motion is associated with the 3D movement of a molecular atom through space. So basically, as you have a molecule inside a container, basically the more space it has to move throughout the container, the more translational motion it has. Okay, so basically 3D motion, okay, is what we're talking about here, right? So let's go ahead and think about this from the perspective of, let's say, a solid versus a gas. Okay, so if we go ahead and we look at the orientations or the setups of the solid versus the gas, what I want you to notice is that the solid is packed together tightly and in close proximity with the other molecules of this particular substance. Okay, and what happens is those molecules sit next to each other and vibrate and move a little bit, but they're constrained to that particular area inside the solid. A gas, on the other hand, has much more spacing between the molecules. It's able to move throughout the container freely until it bumps into the sides. And basically in this situation, the gas is going to have more translational motion. It's going to have more movement options. So because it has more options or more positions, it's going to have a greater entropy than its counterpart in the solid phase. Okay, so greater S is going to be found with the gas. Now, rotational motion is literally the movement of the molecule along an axis. Okay, so a molecule that has a complicated structure is going to have different ways that it can rotate around a particular axis. So the more rotational modes that you have, the more likely you are to have a disordered situation. You have a more complicated molecule. Okay, and then the last one we're going to look at is the vibrational motion. Okay, and the vibrational motion is referring to the specific motion of atoms within a molecule. So basically, the stretching of bonds in a particular molecule. So basically, we're talking about the movement of the atoms along the bonds relative to one another. So you can have stretching where one side of the molecule is stretching, the other isn't. You can have it where both sides of the molecule are stretching, or the atoms are moving away from that central molecule. You also have bending, okay, where you have a movement of the atoms on the outside, basically like an up and down, or kind of like jumping jack type motion. Okay, and so basically these molecules have vibrational motion, which basically creates more disorder, which makes them a little more complicated, and subsequently naturally have more disorder than something that doesn't have quite as many bonds. Okay, so we have translational, rotational, and vibrational motion, and these are all going to potentially contribute to the entropy associated with a specific system. Okay, we're going to go ahead and we're going to look at the relative entropy associated with each of the examples and basically determine which one has the most entropy. Okay, so first example here, we have 2 moles of gaseous HCl versus 1 mole of gaseous HCl. Okay, so basically in this case, the only difference between the 2 examples is the quantity of the substance. Okay, so in this case, remember, entropy is going to be related to the number of arrangements. So something that has more arrangement opportunities is going to be more likely to be spontaneous because it should have more entropy. So in this case, we are going to select the 2 moles of gaseous HCl because there are more molecules, or there is more of the HCl, so it has more opportunities to reach specific states. Okay, so now that we've kind of analyzed that one, let's go ahead and let's look at our next example. Our next example is CO2 solid versus CO2 gas. Okay, so in this case, we're going to be looking at our capability of motion. So in this case, the molecules, again, they're the same type of substance, but in this case, we have different phases. Okay, so we know that the gas phase has basically more options to move. It has more translational motion. Okay, and the more translational motion you have, the more possible arrangements. The more possible arrangements, obviously, the more entropy. So CO2 gas is going to be the phase that is going to have more entropy. Okay, so now let's go ahead and let's move on to our next example. We have nitrogen gas at 1 atm versus nitrogen gas at 0.01 atm. Okay, so one gas is at a higher pressure than the other gas. Okay, so higher pressure usually means smaller volume. So higher pressure giving you a smaller volume means less translational motion. Okay, so we know that the gas at the lower pressure is by default going to have more translational motion, more possible arrangements, and of course, more corresponding microstates. So the entropy of the lower pressure nitrogen gas is going to be higher. Okay, so let's go ahead and let's look at the entropy here. So we have solid sugar and water. They are coming together to form a solution. Okay, so if we look at the solvent, which is water, and the solute, which is sugar, they both have repeating organized patterns in their particular substances when they're by themselves. When we mix them together, we get a distribution of the particles throughout the solution. Okay, so what ends up happening here is we go from more organized systems to less organized systems. So in this case, our entropy of the solution is going to be greater than the entropy of the solute or solvent by itself. Okay, so the solution here is going to be the more disordered system. Why? Because things are spread out and distributed in various different positions instead of this organized system that we see over here. And so our last example here, we actually have 2 different substances. They're both in the gaseous phase. We have 1 mole of HCl and 1 mole of argon. Okay, and so the quantities are the same, the states of matter are the same. Okay, so the translational motion, the quantity related to the possible numbers of positions, all of those things are the same. So why then is the HCl going to have the greater entropy. Okay, and that brings us now to analyzing the molecules. So if we go ahead and we look at HCl versus argon, what you notice that HCl is a molecule that has bonds, and argon is just a simple atom. Okay, and so the driving force here is actually going to be your vibrational modes. Okay, so your vibrational modes here are what's driving the HCl to have the greater entropy. Argon is able to move through space, it's able to rotate along an axis. However, it doesn't have any stretching frequencies because it doesn't have any bonds. Okay, so basically while this hydrogen can move back and forth relative to the chlorine, argon doesn't have that vibrational mode component. So the vibrational modes increase the possible arrangements. Okay, and that leads to greater entropy. So now that we've looked at these examples, let's go ahead and discuss this from the perspective of the second law of thermodynamics. So the second law of thermodynamics states that any spontaneous process is going to increase the entropy of the universe. So basically, we're always moving towards entropy, we're always moving towards disorder, and spontaneous processes are driven by entropy. So basically, if we're increasing the entropy of the universe, the process that we are looking at should be spontaneous. Okay, and this can be related via this equation. So we have the entropy, or the change in entropy of our universe. We have the change in entropy of our system. That's obviously the thing we're placing our focus. Okay, and the delta S of our surroundings is going to be basically everything else. Okay, so obviously the system a lot of times is what we're paying attention to in chemistry, although the surroundings is something that we have to take into account. So delta S of your surroundings is going to be related to the change in your enthalpy of the surroundings and the relative temperature that occurs at. I'm not going to make you do any calculations associated with this relationship, but I just want you to kind of keep it in the back of your head because it's one of the ways that we derive future equations. Okay, now, analyzing spontaneous processes from this perspective of the universe's change in entropy. If the change in entropy is positive, we're spontaneous. If it equals 0, obviously we're at equilibrium. And if delta S of the universe is negative or less than 0, it's non-spontaneous. Okay, so depending on the relative values of our system and surroundings, if we have two positive values, our universe change will be positive, so we'll have a spontaneous process. If they're both negative, they're non-spontaneous. When we start getting into positive and negative signs for our system and surroundings, we start to have to analyze the quantity. So basically the numerical value, not just the sign. So basically in this case, if the surroundings is positive and the value itself is larger, then we're going to end up with a positive value over here. Okay, and so this will be spontaneous. From that same perspective, if the surroundings here are larger in quantity but negative in sign, then we'll get a negative delta S of the universe, and subsequently that process will be non-spontaneous. So now we've looked over spontaneity, we've looked at it relative to entropy, and basically how entropy is the driving force for all processes happening. Okay, and so now that we understand that a little bit better, it's going to allow us to go on to some other concepts.